Okay, let us resume. So far we have been learning about few different types of material. So, we can classify materials based on how they respond to a magnetic field. So, we learned that paramagnetic materials are weakly attracted to magnets, diamagnetic materials are weakly repelled, ferromagnetic materials and ferrimagnetic materials are strongly attracted. Antiferromagnetic materials are also very similar to paramagnetic materials in the sense that they are not strongly attracted. Okay. So, we call only this as ferro or magnetic materials because they are strongly attracted. So, I described how the spin configurations look like in ferromagnetic, ferrimagnetic, antiferromagnetic materials and paramagnetic materials. We did not touch on diamagnetic materials, but that you can do as a homework. So, just take a screenshot, you watch this video later, this is a homework. So, if materials are not strongly responding to, you want to, I will give you the link later. Okay. So, if paramagnetic materials or diamagnetic materials are weakly responding to magnets, how do we measure the magnetic properties? So, typically in most of the labs where they do research on magnetism, we have a magnetometer called a vibrating sample magnetometer. Okay. So, these are sensitive measurement systems with which we can measure very sensitive information about magnetic materials. So, normally you bring magnet next to paramagnetic material, you cannot see the attraction because the force of attraction is not that strong, but with these sensitive magnetometers we can measure the magnetic properties of diamagnetic material, paramagnetic material, ferromagnetic material, antiferromagnetic materials and so on. Okay. So, vibrating sample magnetometer or VSM is a commonly used measurement system for measuring magnetic property. So, when we measure magnetic property, we typically measure the magnetization M as a function of applied field H. Okay. So, you learnt that the magnetization M is the sum of magnetic moments divided by volume or weight mass. Okay. So, we typically measure magnetization or magnetic moment as a function of applied field. Okay. So, here the applied field H is provided by the electromagnet. So, we learnt electromagnet before the break. So, you have coil, then you have a ferromagnetic core. So, the ferromagnetic core produces a magnetic field. So, in this case we have an electromagnet, this is the core, ferromagnetic core. So, the magnetic field either goes from this side to the other side. So, either the field can go this way, or if you change the current direction in the coil, you can make the magnetic field to go from this side to the other side. Okay. So, you can change the direction of the magnetic field, and by changing the strength of the current that you pass through the coil. So, you learn that the magnetic field is this, right. So, if you change the current, the value of the current, then you can change the magnetic field. Okay. So, you can change the direction of the magnetic field and the strength by changing the current direction and the magnitude of the current. Okay. So, typically we can sweep the magnetic field inside this region from say minus 20 kilovolt to plus 20 kilovolt. These are typical values. So, in some equipment maybe this is a 10 kilovolt, some equipment this may be 30 kilovolt. Okay. So, we sweep the field. So, for measuring the magnetic properties, we usually plot magnetic moment or magnetization as a function of applied field. Okay. So, this field can be increased or decreased or changed to another direction and reduced to 0. Okay. So, we can sweep the magnetic field, and we need to measure magnetic moment or magnetization. Okay. So, to measure the magnetic properties, we use Faraday's law of induction. Okay. So, you know that Faraday's law of induction states that if you have a time varying magnetic flux and if there is a pickup coil next to the time varying magnetic flux, you will produce a voltage. Okay. So, this voltage is proportional to the time varying magnetic flux. So, we use this Faraday's law to measure the magnetic property. Okay, so, here you notice that we have the sample. Okay. This orange color one is the sample that we want to measure. Let us say it is magnetized in some direction. Let us say this is north, south, or sorry. Let us say one of them is north, another is south, for example. So, you know that it will generate some magnetic field, right. So, there will be some flux lines coming out of your sample. So, when you vibrate this sample, these flux lines are cutting these pickup coils. So, these blue things that you see, these are pickup coils. So, the pickup coils will see a time varying magnetic flux. So, your sample is the one that produces the magnetic flux and that reaches the pickup coil, and because your sample is made to vibrate, there is a time varying magnetic flux at the pickup coils. So, the pickup coils will generate a voltage. Okay. So, this voltage is the one that you use for the magnetization. For example, what you do is you will put a known sample. For example, you have a piece of nickel. Let us say this nickel sample has 1 EMU. Okay. At first what you do, you place the nickel sample here, you vibrate and look at the voltage. Let us say 1 EMU produces 1 volt. Okay. Then you go back, then you know that 1 volt means 1 EMU. Suppose you get 100 microvolt, then you know that 100 micro EMU. So, you do the calibration with a known sample. So, first you place a known sample, then you know that this particular EMU generates a particular voltage, then you go back. So, if one voltage gives you 1 EMU, then 100 microvolt is like 100 micro EMU, something like that. Okay. So, this is how we measure the magnetization using vibrating sample magnetometer. Okay, typical vibrating sample magnetometer will look like this. So, this is the one we have at NTU. So, this is the magnet, electromagnet. So, the blue color region is the one where we have the coils. So, the coils are wound here, and this shiny silver color thing is the one, the core, ferromagnetic core, and somewhere there we have the pickup coils. Okay. So, the blue color one is the electromagnet, and this shiny thing is the core, and we have some pickup coil somewhere there. Okay. And we place the sample on this vibrating rod. Okay. There is a rod, you can see the sample is somewhere here, and we vibrate this rod using a vibrating assembly. So, this can be a speaker or it can be some electromechanical transducer to vibrate the sample. Okay, so, the pickup coil produces some voltage, that voltage is collected by this system. So, this system will control everything. So, it will sweep the magnetic field, it will collect the signal from the pickup coil, and you can finally get the plot of magnetization versus. So, normally when you measure you get magnetic moment, okay, because you put a sample, if you do not know the weight or volume, what you collect is basically magnetic moment, then later you divide by volume or mass of the sample to get EMU per gram or EMU per cc. Okay.
Sir,
yes.
why we are putting the vibrating rod instead of the fixed rod as stationary rod?
Because you want to produce a time varying flux. So, we are relying on Faraday's law of induction to measure the signal. So, you get a signal only when this magnetic flux of the sample vibrates. Okay. So, you cannot have stationary. Any other question? Okay, so, this cartoon of what is happening. So, you place a sample, sample produces a stray magnetic field, and when you vibrate the sample, you okay, your sample vibrates, then you see that there is a time varying magnetic flux sensed by the pickup coils. So, you see there is some voltage sensed by the pickup coil. Okay. So, this is how you measure magnetic properties. Okay, so far we have been learning some fundamentals of magnetism, but we have not learned like how do different materials respond to a magnetic field. So, I gave you a very simple picture that diamagnetic materials will be repelled by magnet. Okay. But if you place a diamagnetic material inside vibrating sample magnetometer, what property will you see? How will the MH curve will look like? So, all those things we have not learned. So, we will learn that. Then we learnt about ferromagnetic materials a bit. Are there different types of ferromagnetic materials? We have not learnt. Then okay, we make bar magnets from magnetic materials, but why only certain type of materials make them permanent magnet? Why a paper clip is not permanently magnet? So, all those things we will learn in the next few minutes. Okay, first let us go on to learn about how do different magnetic materials respond to a magnetic field. Okay, so, I told you that when we place a sample inside a VSM, we measure magnetic moment or magnetization as a function of applied field. So, let us assume that we are always measuring magnetization, okay, not magnetic moment, but let us say we measure magnetization. Okay, let us say I put a piece of aluminum inside the vibrating sample magnetometer, and I trace the magnetization of aluminum as a function of applied field. So, when the magnetic field is 0, the magnetization is 0. As I increase the magnetic field, the magnetization will start increasing. Okay. So, as I keep increasing, it will go up and it will follow the straight line, and when I reduce the magnetic field, it will just go back to 0 in the same path. Okay. The path is the same. So, this is the typical behavior of paramagnetic materials. So, materials like aluminum, ruthenium, these are all paramagnetic materials. They will show positive slope of MH curve. So, we can define the slope as chi susceptibility. So, in this case basically is m over h or delta m over delta h. So, we use this term susceptibility chi, which is basically the slope of the MH curve when we deal with non-ferro or non-ferrimagnetic materials. So, whether it is a paramagnetic material or diamagnetic material, antiferromagnetic material, we deal with susceptibility. So, do anyone remember where we saw this chi before? Yeah, correct. So, when I showed you the Curie temperature, I showed you this graph and this one. So, this I told you this is magnetization, and from this point onwards is susceptibility. Okay. So, susceptibility is basically the slope of this MH curve, and it is positive for paramagnetic materials. Let us say now I put a piece of copper inside the silicon inside the vibrating sample magnetometer and measure the magnetization as a function of magnetic field. Initially the magnetization is 0, but once I increase the magnetic field, the magnetization will start decreasing. Okay, it will follow this path, and if I start reducing the magnetic field, again it will come back to 0 along the same line. Okay. No, the path is the same for going down and coming back up. So, diamagnetic materials have a negative slope or negative susceptibility. Okay. Ferromagnetic material is a different issue, we will see later. Okay, suppose I give you a piece of material, okay, and ask you to find out whether this material is paramagnetic or antiferromagnetic. How will you find? Okay, that is tricky, right? So, both the materials will have like very weak response to a magnetic field. So, let us say their slope may be something like this. Okay. So, how do you differentiate between para and antiferromagnetic materials? So, for that usually we need to do a temperature dependence measurement of susceptibility. For example, if you measure the temperature dependence of paramagnetic material, you will have this 1 over chi T behavior. For example, at temperature T1 I have this slope, another temperature T2 I have another slope. If I measure the same curve at temperature T3 I have another slope. Okay. So, I have various slopes, okay. Another, let us say T10 I have another slope, something like this. Okay. I mean this is not in order, some random number. Okay. So, I have various slopes, and if I plot the slope as a function of temperature, I will have this curve. Okay. It will follow 1 over T behavior, and this is a typical sign of paramagnetic material. Okay. And if I do the same, I measure this slope, negative slope of diamagnetic material at different temperature, the slope will not change. Okay. The slope is constant. At any temperature, the slope remains the same. So, if I give you some okay. So, constant slope is the indicator of diamagnetism. Constant slope as a function of temperature is an indicator of diamagnetism. Now, let us come back to the question, how will we distinguish between paramagnetic material and antiferromagnetic material. Okay. So, in the case of antiferromagnetic materials, I told you that above certain temperature these materials will not have ordering, they will have paramagnetic. Okay. So, antiferromagnetic materials will behave like paramagnetic materials above certain temperature called Néel temperature, but below Néel temperature their susceptibility has a different behavior. Okay. So, you will see a peak in the temperature dependence of susceptibility as a function of temperature. So, if you see a peak like this is an indicator of antiferromagnetism. Okay, so, I give you a piece of sample. What you do? You go to the lab, measure the susceptibility as a function of temperature. Okay. So, let us say one sample gives you this behavior, okay, another sample gives you this behavior, then you can say that this green sample or one that gives the green line is paramagnetic, and the one that gives you the red color behavior is antiferromagnetic. Okay, so, this is how you can distinguish between paramagnetism and antiferromagnetism. So, this peak is an signature of antiferromagnetic materials. You can skip this one. Okay, let us do some questions. Okay, most of you are right. We have some work on the basis of Faraday's law. Okay, next question. Okay, positive susceptibility is from paramagnetic material. Majority of you are right. Next one. Okay, most of you are right. Okay, so far we have learnt how the MH curves of different materials like paramagnetic, diamagnetic and antiferromagnetic materials will look like, but we haven't learnt how the MH curve of ferro or ferrimagnetic materials will look like. Okay. So far the cases were either they were increasing or decreasing as a function of magnetic field. Okay. But if you place a ferromagnetic or ferrimagnetic material inside a vibrating sample magnetometer and you try to measure the MH curve, it will not be a straight line. Okay. It will show a different behavior, what we call hysteresis loop. Okay. Okay, so let us say you start, let me stop here. Let us say you start increasing the magnetic field. Initially the magnetization will increase to certain value. Okay. It will not go straight line, it will go in some curved line, it will go up. Okay. Then you reduce the magnetic field. It is tracing a different path. Okay. Now you go to the other direction, you reduce the magnetic field, again it traces another path. Okay. So you see that it creates a loop. Okay. And this loop is called the hysteresis loop. Okay. So this is a typical behavior of ferro and ferrimagnetic materials. Okay. So you start from here, for example, 0 magnetization. As you increase magnetic field, you see that it goes in a non-linear fashion. It reaches the saturation, and when you reduce the magnetic field, it takes another path. Okay, it reaches saturation in the other direction. You reduce the magnetic field, then change the direction. You see that it traces another path. So basically, you have a loop, and this loop is called hysteresis loop. And this is a typical behavior of ferro and ferrimagnetic materials. So from this loop we can extract many different parameters, and these are very useful parameters when you design a material for magnetic recording or material for MRAM application. These parameters that you get from the hysteresis loop are very important. Okay. So the first concept that you need to learn is saturation magnetization. So usually shown by this symbol MS, means saturation magnetization. So when you apply sufficiently large field, so very large field, then the magnetization of a sample reaches saturation. Okay. It increases, then at some point it saturates. Okay. So this saturated value is called saturation magnetization, and when you reduce the magnetic field, so you are reducing at this point, the magnetization is 0. Applied field is 0. There is no 0, there is no magnetic field, but still some magnetization is remaining in the same direction. Okay. So this remaining magnetization is called remnant magnetization. So remnant magnetization MR. Then let us say you change the direction of magnetic field, reduce, you keep, now you are changing the magnetic field in the other direction. So at some point of time, the magnetization becomes 0. Okay. So when you see a hysteresis loop, it has 4 quadrants. This is typically 0 0. Okay. This is typically 0 0, means the magnetization is 0 and the magnetic field is 0. Okay. This coordinate means magnetization is 0, field is also 0. So, typically this side is a positive field, this side is a negative field, and this upper side is a positive magnetization and this is negative magnetization. Okay. So, when you come to this field, the magnetization is 0. Okay. So, y axis is magnetization, x axis is H. So, y axis is 0, which means magnetization is 0. Okay. So, this field, you can see this is a certain field, right. So, this field at which magnetization becomes 0 is called coercivity. So, this is another important parameter, and if you go further, again you will reach saturation. So, the magnetization saturates again. Okay. So, this value and this value are same, but different magnitude. Okay. Either you call this as saturation magnetization or call this as saturation magnetization. This will be symmetric. And normally this is also symmetric. Okay. There are some cases where this H c is not symmetric, but normally the coercivity also is symmetric. Okay. So, you can imagine this loop now, you have MS, MR and coercivity. These three are very important parameters. So, usually what I do is ask my students to close the eyes, trace hysteresis loop in your brain, then assign these 3 points MS, MR and coercivity. Okay. These are very important parameters. Okay. So, by placing a ferro or ferrimagnetic material inside a VSM, we can trace this loop and get these parameters like MS, MR, coercivity and so on. So, in some field, for example, magnetic recording, we also have another field called nucleation field. So, at this field what happens, the magnetization at this field is actually 95% of saturation magnetization. Okay. So, this may not be that important, but these three are very commonly used terminologies. MS, MR and coercivity are important. Okay. So, let us do a recap of what we learnt about hysteresis loop. Yeah, the book lab shows some other question not shown in this picture. Let us do the book lab question. Okay, it's open now. Okay. Only 4 of you are right. Only 4 are right. So, which 4? This one or this one? Huh? Yeah. So, only 4 of you are right. So, usually this question helps me in understanding whether whatever I am teaching is going there or not. Okay. So, let us come back to this. Let us imagine that the sample you have has 100 particles. Okay. For simplicity, maybe let me draw like 9 particles, 16. Okay. So, when you apply very high magnetic field, so imagine each square is one particle. Okay. So, when you apply very high magnetic field, all the, okay, let me use this symbol and this symbol to represent magnetization into the TV or out of the TV. Okay. So, when you apply magnetic field in this direction at high field, all are pointing into the board. Okay. Now, you come to this point. Okay, that means the field is 0. This MR is slightly lower than MS. So, what could happen is that out of this 16, maybe one of them is now this direction. The remaining all are still the magnetization of the remaining 16, remaining 15 will be pointing into the board. Okay. Now, when you come here, M is 0. So, M is 0 means what? Like 8 of this is pointing in this direction, 8 of the remaining units are pointing in the opposite direction. Only then the net will be 0, right. So, by applying this coercivity, you are reversing only half of these whatever magnetic units into the other direction. Okay. So, when you apply very large magnetic field, then again all 16 will be having magnetization in this direction. Okay. So, this field is called the saturating field. Usually people use the term HS. So, HS is the field where you magnetize all the grains or whatsoever into one direction. So, in coercivity you are only switching half of the magnetization. Okay, so, coercivity is the field required to reverse half of the magnetic moments. So, out of the 16 you have only reversed 8 of them, as a result you get 0 magnetization. Okay, next question, this one we will do later, not taught yet. I want to find out where is this question. Okay, now we'll do this question. Any question from online?
There is one question.
Okay.
If not moments, then what are we measuring in the paramagnetic region?
If not moment, what are we measuring in the paramagnetic
Regions.
region?
Last session question.
Huh?
Last session question. Before break.
Before break, what was the question?
Like in the paramagnetic
Okay.
region, if you are not measuring the moment, then what we are measuring?
You are measuring the moment only, right? I don't know. Okay. Okay, point A is saturation magnetization. Almost all of you are right. I want to see like 100% correct for this kind of simple questions. Anyway, mostly correct. Next one. Okay, some of you didn't do the visualization exercise, more wrong answers. I think we are closer to lunch time. Okay. The correct answer is coercivity. Next one. Okay, most of you are right. Okay, so far we have been learning about how the magnetic materials will respond to magnetic field when we place them in VSM and measure the MH behavior. Okay. So, we learned how the ferromagnetic materials will behave. So, maybe we will briefly discuss this one, then go for lunch. Okay. So, the next question that I am going to answer is are there different types of ferromagnetic materials? Okay. Yes, I mean based on how they respond to magnetic field, we can classify the ferromagnetic materials or ferrimagnetic materials into two types. So, one is called hard magnetic material and another is called soft magnetic material. Okay, so, this is nothing to do with the mechanical hard or soft property, but this is related to how easy or how hard it is to demagnetize the material. For example, if you take a paper clip, right, you as a child you would have tried to magnetize the paper clip. So, paper clip after you magnetize for certain time, it would be attracting some other magnetic material, but after some time you will notice that the paper clip has lost its magnetic poles, it does not attract magnets anymore. Okay. On the other hand, if you go to say a shop, buy a strong permanent magnet, that permanent magnet will retain its north south polarity for many years. Okay. So, based on how the magnetic remanence is retained, we can classify the materials into two types, hard and soft. Okay. So, we are looking at two properties. Firstly, the retention of the magnetization, because that is what determines the north and south poles, the permanence of the north and south poles. Okay. So, for example, if you magnetize a paper clip, okay, after some time its remanence will be very low. After some more time it may even come back to 0, that means it has lost its magnetic north and south poles. On the other hand, the neodymium iron boron type of magnet that you buy from say some shop, they will retain the north, let us say this is the north pole, this is south pole. So, they will retain that for very long period of time. So, the retention is one thing. So, the hard magnetic materials retain this magnetization with respect to MS for long time. The second and the most important property is the field required to demagnetize or field required to change the polarity from north to south. For example, if I have a paper clip again, so this is a paper clip, initially this is north, this is south. Now, I want to apply some magnetic field and change this to south and this to north. Okay. So, the field I require to change the polarity will be very small. So, typically very few oersted is enough to change the polarity of a paper clip, because paper clip is made of a soft magnetic material. On the other hand, if I have a neodymium iron boron magnet, it is a permanent magnet. If I have to change the north pole to south, south pole to north, I need to apply very strong magnetic fields. So, typically like 10,000 or 20,000 times larger magnetic field to change the polarity of a neodymium iron boron magnet. Okay. So, the coercivity or the MS or the field needed to reach this particular point will be very large for the permanent magnets. Okay. So, these two are the important properties that distinguish between hard and soft magnetic materials. So, we cannot say that these materials do not retain magnetization and they are useless. Okay. They have their own use. Okay. So, in some many applications we do not want the magnets to retain the polarity. For example, if you are talking about transformers, so in transformer you have like a core, then you have input coil, output coil. So, you magnetize and demagnetize the transformer core many times. Okay. And this loop is basically the energy product. So, if this loop is wider, every time you magnetize and demagnetize a transformer, you are spending a lot of energy. Okay. So, in applications like transformer and electromagnets, you want a soft magnetic material which does not retain magnetization or which has like almost 0 hysteresis loop. That kind of property you need for some application. For some other application where you want to retain two states, for example, you are talking about magnetic recording or MRAM. So, you are talking about two states. So, let us say this is a 0, this is 1. So, you want two states. So, you want these two states to be like not easily changed from one to other. So, you want large energy. So, the area under hysteresis loop is a kind of energy spent to magnetize and demagnetize. So, this energy will be larger in the case of permanent magnets. and permanent magnets have their own application. So, when we are talking about recording memory or permanent magnet application, we want materials with hard magnetic properties. So, we can classify ferromagnetic materials into two types and they have their own applications. So, if you talk about the writing head used for writing information in magnetic recording, that uses soft magnetic materials.
Sir,
Yes.
in the previous slide for the hard chromatic material, the MS value is between low to moderate. What does that mean?
Okay. I mean, if you compare the MS value of many hard magnetic materials with soft magnetic materials, you will usually find that soft magnetic materials have a large MS. Relatively, hard magnetic materials will have a low or moderate value. Okay, I will give you some number. If you take pure iron will have like say 1007 or 2200, I don't know, somewhere here mu per cc. So, if you alloy iron with cobalt, you can, I mean, for certain composition you can go all the way to 2000 mu per cc. So, these are typical values of soft magnetic material. But if you take say neodymium iron boron or some such material, the MS will be around 800 mu per cc, something like that. So, you see that this is the not that high compared to this. So, that is the meaning. So, typically the soft magnetic materials have a large MS, comparatively these materials will have low to moderate. I told you that the old speakers have black magnet. So, those are ferromagnetic materials, they are hard magnetic material and their MS will be only around 300 mu per cc, something like that. Yeah.
What is the key parameter that dictates if it would be a hard or soft magnetic material?
What property keeps the material to be soft or hard, is it? Okay, which will come to that later. Yeah, maybe tomorrow. And after a few minutes, we will break for lunch. Then tomorrow we will discuss that. Anything else? That is the immediate next topic. Okay, so I mean the definition of hard or soft is also relative. Okay, so there is no boundary line that beyond this is soft, beyond this is hard. No, nothing like that. So we are talking about relatively hard, relatively soft kind of thing. Okay, so here I give you some number about the coercivity values, for example. So, if you take neodymium iron boron, which is a hard magnetic material, they have a coercivity of around 1.5 Tesla. If you take a piece of iron, it has a very low coercivity of 0.0001. If you take a piece of pomalloy, which is an alloy of nickel and iron, so the coercivity is even lower. Okay. So, you can see the difference in coercivity values between a soft magnetic material and a hard magnetic material. So, if you wonder what is a Tesla, okay, to give you some feeling of Tesla, I have given some numbers here. For example, you measure the magnetic field of the earth, which is sufficient enough to orient a compass in certain direction, that has a field of around this one. A neodymium iron boron magnet can generate easily between 0.0 0.1 to 0.2 Tesla. And if you have seen NMR equipment, they have like huge magnets with the superconducting magnet. They can generate 5 Tesla kind of field. Okay. I mean, to give you some idea of how strong the magnetic field can be. So, you might have heard about this incident that in one of the hospital, the attendant carried a gas cylinder inside the MRI room. So, this magnet, 5 Tesla magnet, pulled him along with the gas cylinder. Okay. So, that is the power of this kind of magnetic field. Okay, the reason for the soft and magnetic property is coming next, but we do not have time to finish that today. So, we will end here, then you can go for lunch, then we will see again tomorrow. Okay.
Question from the online participant.
Okay.
From the hysteresis, how do we differentiate the ferromagnetic, ferrimagnetic and antiferromagnetic?
That is a very tricky question. It is not that easy. Okay, so how we can, that is a tricky question, maybe I will answer tomorrow.